Now, additional exercise, example 3.23. A three-wheeler starts from rest, accelerates uniformly with 1 meter per second square on a straight road for 10 seconds and then moves with uniform velocity. Plot the distance covered by the vehicle during the nth second versus n. What do you expect this plot to be during accelerated motion? A straight line or a parabola? Okay. Now see here, distance traveled in nth second. For that we have the equation, that is v0 plus a by 2 into 2n minus 1. Here it start from rest means initial velocity, that is 0, acceleration, that is 1 meter per second square. So we can write 1 by 2 2n minus 1. So d nth, that is 1 by 2 2n minus 1 will give you n minus 1 by 2. Means d nth, distance traveled in nth second, directly proportional to n. So obviously the graph, that will be a straight line graph. Now to plot the graph, take different seconds, first, second, third, fourth, fifth, and substitute the values of nth second in this equation, n minus 1 by 2, and take d nth. So when you substitute n equal to 1, d nth, that is 0.5. When you substitute n equal to 2, so 2 minus 1 by 2, 1.5. Then when you substitute n equal to 3, then 3 minus 1 by 2, 2.5. Like that, you can calculate d nth. Now from this data of n and d nth, you can plot the graph, and the graph will be a straight line like this. Clear? And that graph, that will be a straight line like this. Clear? Now see here, what do you, sorry, tap to 10 seconds. Okay, now we have to plot the graph simply, and after 10 seconds, if we want to calculate the velocity, then you can use the equation v equal to v0 plus at. So velocity, that will be 10 meter per second. So after 10 seconds, it move with constant velocity. Clear? So this one is the case. Now example 3.24. A boy standing on a stationary lift open from above throws a ball upwards with the maximum initial speed. He can equal to 49 meter per second. How much time does the ball take to return to his hands? If the lift starts moving up with a uniform speed of 5 meter per second, and the boy again throws the ball up with the maximum speed he can, how long does the ball take to return to his hands? Now see, lift is a stationary, and the boy throws a ball with initial velocity 49 meter per second. When it reaches at the maximum height, its final velocity will be 0. Clear? Now, acceleration, that is gravitational acceleration. So now we have to calculate the time to ascend. Okay. Now, v, that is v0 plus at. So we can write 0, that is initial velocity 49 acceleration, that is g minus 9.8 into t. So 9.8 t, that is 49. Therefore, t equal to 49 upon 9.8 will give you 5 seconds. Now time to ascend, the same one is time to descend. It implies that once the ball is thrown and the time after which it returns to the hands of the boy, that is the time to ascend plus time to descend, but both the time, that is same one. So we can write total time, that is 5 plus 5, that is 10 seconds. Now second case, when the lift is moving with uniform speed. So when the speed is uniform and the same phenomenon is repeated, then the same time will be there to come back to the hand of the boy. Why? Because when lift is moving with uniform speed, it implies that acceleration is 0. And when acceleration is 0, then there will be no effect on the motion of the ball. Clear? Now example 3.25. On a long horizontally moving belt, a child runs to and fro with a speed 9 km per hour with respect to the belt, between his father and mother located 50 meters apart on the moving belt. The belt moves with a speed of 4 km per hour for an observer on a stationary platform outside. What is the speed of the child running in the direction of motion of the belt? B. Speed of child running opposite to the direction of motion of the belt. And C. Time taken by the child in A and B. Now, which of the answers alter if motion is viewed by one of the parents? Now, see. Now, velocity of child, that is 9 km per hour, velocity of belt, that is 4 km per hour. Now, we want to calculate the speed of child when child is running in the direction of the belt and observer is outside it, means observer is on the steady platform. So velocity of child with respect to belt, that is Vc plus Vb, because the frame of reference belt and the child both are moving in the same direction. So for the observer outside it, the resultant speed of the child that will be observed somewhat increased to 1, and that is Vc plus Vb. So that is 9 plus 4, 13 km per hour. Now speed of the child running in opposite direction of the belt. Simple. So with respect to observer which is on the platform, we can write VCB, that is Vc minus Vb, 9 minus 4, that is 5 km per hour. Now time taken by child in A and B. Okay. So time taken by child to move up to father or mother, but father, mother both are on the same belt. It implies that for child, father and mother, when the frame of reference that is the same one, it implies that to reach up to father or mother, child have to cover the same distance 50 meter and with speed 9 km per hour. So when velocity of child, that is 9 km per hour, so 9 into 5 by 18, 2.5 meter per second. Now child have to cover the distance, that is 50 meter with speed 2.5. So time taken by child, that will be 50 by 2.5, that is 20 seconds. Now say Which of the answer alter if motion is viewed by one of the parents? Then answer A and B will be changed, but this time will not be changed. Clear? Now example 3.26. Two stones are thrown up simultaneously from the edge of a cliff 200-meter high with initial speeds of 15 meter per second and 30 meter per second. Verify that the graph shown in figure 3.27 correctly represents the time variation of the relative position of the second stone with respect to the first. Neglect air resistance and assume that the stones do not rebound after hitting the ground. Take G equal to 10 meter per second square. Give the equations for the linear and curved path of the plot. Now, the graph of relative position x2 minus x1 versus time, that is given to you. Up to 8 seconds, the graph is a straight line, and then 8 to 10 seconds, it is parabolic one. Now, we have to justify this one with the help of equations. See, we have the equation for the position of the particle moving with constant acceleration, that is x equal to x0 plus v0 t plus half at square. This equation will give you the position of the particle at any instant t. x0, that is its initial position, v0, that is initial velocity, a, that is acceleration. Now, position of particle 1 at time t, that is x0 is 200, v0 that is 15, a that is minus 10. So we will get the equation x1 equal to 200 plus 15t minus 5t square. Now position of particle number 2 or stone 2 at any time t, that is x2 equal to 200 plus its initial velocity, that is 30. So 30t plus half minus 10 into t square. So x2 equal to 200 plus 30t minus 5t square. Now position of 2 with respect to 1. So that is x2 minus x1. So x2, that is 200 plus 30t minus 5t square minus 200 plus 15t minus 5t square. Now if we solve this one, we will get x2 minus x1, that is 15t. So x2 minus x1 directly proportional to time t, here we can observe. It implies that now we can understand the graph of x2 minus x1 versus t, that is the straight line. So this is the straight line graph, but it is straight line up to 8 seconds only. Clear? So let's calculate time taken by the stones to hit the ground. So when stone hit the ground, their final position, that is 0. So when stone hit the ground, x equal to 0. So for first stone, we can write x1, that is 200 plus 15t1 minus 5t1 square. t1, that is the time taken by first stone to hit the ground. And when it hit the ground, x equal to 0. Then after, we can write this equation like this: 5t1 square minus 15t1 minus 200, that is 0, multiplied by minus 1 on both the sides. Simple thing. Take 5 common from this equation, take it on right hand side. So we'll get t1 square minus 3t1 minus 4t, that is equal to 0. Now solve this equation, we will get t1 minus 8 into t1 plus 5, that is equal to 0. So we'll get t1 equal to 8 seconds or t1 equal to minus 5 seconds. But value of the time minus 5 seconds. That is not permissible. Therefore, we can write T1 equal to 8 seconds. Means after 8 seconds, first stone fall on the ground. It implies that after 8 seconds, now motion of the second stone, that is absolute one, individual. Okay. Now see, x2, that is equal to 200 plus 30 T2 minus 5T square. So here see, this equation suggests this thing, x2 that proportional to T2 square. Position of first one, that is on the ground, means 0. It implies that now the graph that will be parabolic one, because x2 proportional to T2 square. Now solve this equation. 5T square minus 30 T2 minus 200, that is 0. Take 5 common, take it on right hand side. So T2 square minus 62 minus 40 equal to 0. So we'll get T2 minus 10 into T2 plus 4, that is 0, means time taken by second stone to hit the ground, that is 10 seconds. And yes, we can observe here at 10 seconds, the position is 0. Clear? So graph is discussed. Example 3.27. The speed time graph of a particle moving along a fixed direction is shown in figure. Obtain the distance traversed by the particle between A, t equal to 0 second to t equal to 10 second. B, t equal to 2 second to 6 second. Part 1, question A, that is simple one. Say, velocity time graph. So for that we already discussed the area under the graph that will give you the distance traveled. So distance traveled in time 0 to 10 second. So for this particular graph, for 0 to 10 second, we have to find the area under the graph with respect to time axis. So that distance traveled, that is area under the graph. That is area of triangle A, B and C. That is half into base into height. So half into AC into BD. So half into AC, that is 10, and BD, that is 12. So you will get 60 meter. But now to find out the distance traveled in 2 to 5 seconds, sorry, 2 to 6 seconds, that we have to calculate in two parts. Why? Because see here, at 5 seconds, which is between this time interval, 2 to 6 seconds, the motion is changed. The motion is changed. Clear? Now see, here we can observe up to this one. B means up to 5 seconds the velocity increases, and then after velocity decreases. Clear? So up to 5 seconds the motion is accelerated one, and after 5 seconds it is decelerated one. So first we will calculate the distance traveled in 2 to 5 seconds, and then after we will calculate the distance traveled in 5 to 6, means in raised to 1 second, and then after we will take the summation of this one, will give you the total distance traveled in 2 to 6 seconds. Got the idea? Okay, now see, let's start. Initial velocity, that is 0. Acceleration, that is the slope of this graph, that is 12 by 5, 2.4 meter per second square. Now, to calculate the distance traveled in 2 to 5 seconds, first we have to calculate the total distance traveled in 2 seconds. So we use the equation x equal to v0t plus half at square. Now distance traveled in first 2 seconds. So that is x1 equal to initial velocity 0 plus half acceleration 2.4 and in 2 seconds, so t equal to 2 square of it. Solve this one, you will get 4.8 meter. Then after calculate the distance traveled in total 5 seconds. So t equal to 5 seconds. So x2 equal to 0 plus half into 2.4 into total time 5 seconds square of it. That is equal to 1.2 into 25 will give you 30 meter. It implies that now the distance traveled in time interval 2 second to 5 second. 2 second to 5 second. That is 30 minus 4.8. 30 that is the total distance traveled in 5 seconds. 4.8 that is the total distance traveled in 2 seconds. So distance traveled in 2 to 5 seconds, that is 30 minus 4.8, that is 25.2 meter. Now think about 5 to 6. So at 5 seconds we have the velocity 12. So now we can consider this one as initial velocity. So V0 dash, that is 12 meter per second A dash. So now the slope of this graph BC, the same one, 2.4 meter per second square, but negative because velocity is now decreasing. Now we have to take distance traveled in 1 second 5 to 6. Here we can take distance traveled in 1 second because we have the initial velocity at 5 seconds. Clear? Now x dash equal to V0 dash, that is 12 into time 1 second plus half into acceleration A dash, that is minus 2.4 into 1 square. So this will give you resultantly 10.8 meter. So total distance traveled in time t equal to 2 second to t equal to 6 second. That is this 25.2 meter plus 10.8 meter. Resultantly, you will get 36 meter. So average speed during this motion, that is path length, means total distance traveled upon time interval. So total distance traveled, that is 36 meter. Time interval 2 to 6 seconds, so that is of 4 seconds. So 36 by 4, you will get 9 meter per second, that is the average speed. Now example 3.28. The velocity time graph of a particle in one-dimensional motion is shown in figure. Now, which of the following formula are correct for describing the motion of the particle over the time interval t1 to t2? First formula, x at time t2 equal to x at time t1 plus v at time t1 into t2 minus t1 plus half a t2 minus t1 square. Now this one is the equation for the position at time t2 for motion with constant acceleration. See here, between t1 to t2, the graph of velocity versus time is not a straight line graph. It implies that the slope of this graph is not constant one. It implies that acceleration is not constant one. It implies that we can't use this equation for time interval t1 to t2. Okay, so this equation is not correct for describing this motion. B, v at t2 equal to v at t1 plus a into t2 minus t1. Again the same reason. In this interval acceleration is not constant, so this one is not suitable to explain this motion. C, V average, that is x t2 minus x t1 upon t2 minus t1. Yes, this is generalized equation for any type of motion, whether the acceleration is constant or not. Okay, so that is as per the definition of average velocity. So we can use this equation to describe any damn type of motion. Then D, A average, that is equal to V T2 minus V at T1 upon T2 minus T1. Yes, this equation that we can use, because this one is as per the definition of average velocity. Clear? Any type of acceleration is there, we can use this one. Then E, x at T2 minus x at T1 plus V average into T2 minus T1 plus half into A average into T2 minus T1 whole square. No such relation is there, including average velocity and average acceleration. No such equation is there in physics, so we can't use this one. Then F, x at T2 minus x at T1, that is equal to area under the velocity time curve bounded by the t-axis and the dotted line shown. Yes, because area under the graph of velocity versus time give you the distance traveled in the given time interval, irrespective of the shape of the graph. So we can use this equation to explain this motion. Clear to all of you? Chapter 3 is completed.